So what we're going to do now is we're going to talk about Java 8 streams. This is a topic, once again, we've been covering in dribs and drabs throughout the course, but haven't really looked at it in any systematic way. So in this part of the lesson, we're going to talk about the structure and functionality of Java 8 streams, focusing on the fundamentals of streams. So what the heck is a stream? A stream in Java 8 is an ordered pipeline of so-called aggregate operations that process a conceptually unbounded, though usually bounded in practice, sequence of elements. All right, so that's a definition. That whether that enlightens you in any way, shape, or form may not be clear, but we'll talk more about that in a second. So some example of aggregate operations, which are operations that modify the flow of data through the stream, include filter, map, for each, and collect. You've seen for each before. We've talked about filter, map, and collect briefly, and we'll go into that in more detail. So the key thing is that you've got these aggregate operations that are going to manipulate the flow of data through the stream. So the aggregate operation performs a function on each element in the stream. And a function can be implemented by a lambda expression or a method reference. So the things we talked about before start applying. Ideally, although there are some exceptions to this in practice, although in theory you never want there to be exceptions, but sometimes reality rears its ugly head. Ideally, a function's output in the stream should depend only on its input arguments. So you can see, as shown here, you want to have ideally you want to have the function that's called on this input only modify things internally and then produce an output and not have any side effects. And you can take a look at this link to learn more about so-called pure functional programming. The more you can stick to pure functional programming, the easier it is to reason about your program, number one, and the easier it is to transparently speed it up on a multiprocessor. A stream, unlike a collection, which they're related to, as we'll see, a stream holds no non-transient storage. So basically, a stream is just data in motion. So it may get washed away with the next wave, right? You shouldn't expect it to stick around unless you do something to make it stick around. Every stream works in essentially the same way. It starts with a source of data, which is the input. It processes the data through a pipeline of these intermediate operations, which are these aggregate functions. And it finishes up with something called a terminal operation. And there's some really interesting subtleties to the difference between an intermediate operation and a terminal operation, as we'll see shortly. The terminal operation, and there can only be one terminal operation, triggers the processing of all the other aggregate operations in a stream, including itself. So in other words, no work gets done until the terminal operation is called, and then all the intermediate operations get run. And the reason for doing this is it allows certain kinds of cool optimizations, as we'll see later. By default, each aggregate operation in the stream runs its function sequentially. So by default, there's one and only one thread. And we'll talk later about how to go ahead and enhance that. This discussion will be sequential streams. And parallel streams will be covered later if we have time. If we don't have time, there's other places to learn about that. So it turns out that Java 8 streams are basically the implementation of a classic pattern called pipes and filters, where you connect an input device with some kind of output device through a series of filters that transform the flow of data that goes through the pipes. And so this pattern basically divides an app's task into multiple self-contained data processing steps, which are the filters, and connects these steps together via intermediate data buffers to form the data processing pipeline. So what are some examples of this? If you're this is where you can find out about the book where this appears is in volume 1 of the POSA series, and there's also an article here you can read about it. Other common implementations of pipes and filters include a pipeline in the Unix shell. So if you use Linux or if you use Mac OS, you may know about the pipeline concept, where you can pipe the output of one program as the input into another. You can rearrange things very cleanly using pipes. And there's also something called System 5 streams, which is a similar kind of idea, except for layered protocol stacks. So those are two other examples of pipes and filters patterns in practice. OK, so that's just a quick overview of what streams are. All right, so part 2 of Java 8 streams. Now we're going to talk about some of the common stream aggregate operations. These are the things that are used to transform or manipulate the data as it flows through the stream. The features we're about to talk about applied both to sequential and parallel streams. So what you learn here will be transferred when we start talking about parallel operations. So recall that an aggregate operation is used to process all the elements in a stream. So here's some examples. So we might have input that comes in, and we might apply various aggregate operations to that input. So the first method we're going to look at is called map. And map is basically an aggregate operation, an intermediate operation, that applies the given function, called the mapper function, to each element in the input stream. And it's going to return, as the result of map, an output stream that consists of the results of applying the mapping. So another name for map might have been transform, because you're typically going to transform the stream in one way or another. And one of the things to remember with map is that the number of elements in the output stream that comes back from map must be the same as the number of elements that went into the stream. So it's going to transform each element by applying the function. So if there's 10 elements coming in the stream, you'll get 10 results coming back. They don't have to be, by the way, the same type. So map may also do some transformation to take one set of input and then return the same number of things with different types. Filter, in contrast, applies a predicate against each element of the input stream, and it'll return an output stream that consists only of the elements that actually match the predicate. So it's basically a way of filtering stuff out. Think like you're panning for gold or something like that, and so you pour stones or rocks into your pan, and you filter out the stuff you don't want. So in this case, the number of output elements from filter may be less than the number of input elements. If something doesn't match the filter, it doesn't come out. It's stopped. Map and filter are these intermediate operations. They process elements in their input stream, and they yield an output stream that's then passed on to the next phase or the next part of the pipeline. Something else that's really important to remember, these intermediate operations are lazy, and they don't actually run until a terminal operation is reached. So it's only when we reach the one and only terminal operation that any of the intermediate operations run. And that's there to enable certain types of optimizations. A terminal operation is one that actually does the processing. It kicks off, it initiates the processing, and then does something to finish the stream. Here's a particular example that uses a collector. So collect uses a collector to perform a so-called reduction on the elements of its input stream, and it'll return the results of the reduction. Now, in this particular case, what we're often doing is we're often reducing things to transform them, filter them, and then return, say, a list or a table or a map of something. That's one type of reduction. There's other type of reductions where you'll take a bunch of input elements and return one value as the result. That's kind of a map-reduce-like approach. Because this is a terminal operation, it also triggers all the other operations in the stream, all the intermediate operations, to do their thing. Each stream must have one and only one terminal operation. If you forget to put a terminal operation on a stream, it just won't run. And when I first was playing with streams, I would write my program, think it was great, and then I would look at it, and it wouldn't produce any output. I'd be like, why is that? Well, the reason was I'd forgotten to put a terminal operation at the end. Collect is one example of a terminal operation. For each is another example. Those are two very common examples of terminal operations. So now that we've talked in general about what a stream is, and I've kind of given you a formal definition and described a couple of its aggregate operations at a high level, let's take a look at a specific example. And this is going to be creating something we call the Search StreamGang program. And you can find the implementation here. And this revises an earlier version of another program that used Java Executor framework to do some concurrent processing, which you can also take a look at if you're curious. So let's take a look at this. So here's the search StreamGang. The search StreamGang is going to take a bunch of input strings to search and a bunch of search words to look for in the input, and it's going to go ahead and use a stream to be able to look for those words in the input. And the first version we're going to look at is a purely sequential version. If we have time later, we'll talk about the concurrent version, which is almost identical, but it runs concurrently as opposed to running sequentially. So you could use this if you were, you had a bunch of text documents and you were searching them for keywords or other markers or something like that. So we're going to find the words and a list of input strings. So we're going to take a look at two methods, process stream and process input. And as you can see at a very high level, both of these things use streams, and we'll talk more about how they work as we go through here. And you can actually take a look at this file to see this code. As you'll see, we're going to focus on a few of the aggregate operations, particularly map, filter, and collect. There are other operations as well, but those are some of the ones you see all the time. OK, so let's take a look at process stream. So process stream is going to be used to sequentially search for words in a list of input strings. And here's how it's going to work. As you can see here, process stream is a method that returns a list of search results. And so what it's going to do is for every input string that we're going to look at, because you might have 10 different input strings, which could be files, right? 10 files, whatever. It's going to go ahead and give us back a list of search results for the things we looked up in each of the files, or each of the input. So the way this is going to work is we are going to use a very short stream pipeline to do all this for us. And you'll notice right away as we go through this, this is very declarative. We're not saying how to do it. We're saying what we want to have done. And here's how it works. We first get the list of input strings as a stream. So get input is going to return a list of input strings to search. So take it on faith that get input returns a list of strings. We then go ahead and take that list of strings and we convert that list of strings into a stream. And it turns out that this method stream is what's called a factory method. And you can call stream, or .stream more specifically, on a collection, like a list or a map or whatnot. And it will give you back what's known as an internal iterator. It'll convert that collection into a stream. And we'll talk later about other ways to create streams. So we've converted our collection, our list, into a stream. And then for every element in the stream, which is a stream of strings, we're going to call a method reference called process input. And we'll talk about that method in a second. And what that's going to do is it's going to give us back, so what you can see here, this is taking a stream of strings, and it's mapping that stream of strings into a list of search results, where each list contains a match, if any, for every search word that appeared in each of the input strings. So we're basically saying, call the process input method and convert the input strings into a list of search results. And then we take the results of that, because process input returns a list of search results, one list for each input string. And then we're going to take that and we're going to call collect. Remember, collect is the terminal operation. And collect is going to run this stream, and it's going to take every element that comes out of map, and it's going to coalesce it or reduce it into a list. So that's what toList does. And so you can see that it's going to take a list of search results for each element that came out of map, and it's going to create a list of search results. So for every input string, we'll have a list of search results. And since we had a list of input strings, we'll end up with a list of search results. OK. So the key thing to note about this is how declarative it is. It doesn't say how any of this works. It just says, here's what I want you to do. Convert a list of input strings into a stream, map each element by calling process input, and collect the results and return a list. All right, so let's take a look now at process input. This is the guy that actually does the heavy lifting, actually does the searching. So process input, as you can see, it takes a string that we're going to search, and this input that comes in here is managed by the driver program that runs this whole thing. So my particular example I have here, I think, is Shakespeare plays. So I took like Hamlet or Macbeth, and I broke each act up into a separate string. And then I would go and I would search for words in that act, just to do something interesting. You could do all kinds of other stuff too. So we split things up. We get the title, and then we go ahead and get the input. The input's actually the content. And then what we do here is we have a list of words we want to find. So we take the list of words to find, and we convert that into a stream. So for every word we want to find in our list of words to find, we then go ahead and call map. And what we do is we take the word, remember, let's say, again, just to be simple, we're going to have words that are the names of the musical notes, do, re, mi, fa, so, just to give us some words to search, right? So for every name of words of musical notes, we're going to take each word corresponding to the note, and we're going to go ahead and we're going to call this function search for word, and it's going to go ahead and look for the word in the input string. And it's going to create, as a result of that, a list of results, right? List of search results. Now, it may turn out that the particular input string we're searching has none of those words at all, in which case we're going to get back a search result that has the size of 0. We don't care about strings that don't have the words we're interested in. So in that case, we're going to go ahead and filter them out. So we're going to get back a stream of search results, and we're going to go ahead and filter out anything that doesn't have items in it. So if there was nothing was found, if we didn't find any of the search words in that particular input, it gets removed altogether. We just ignore it. For anything that did return something, for any string that did have the words we were looking for, we're then going to go ahead and collect the results into a list. So we'll end up with a list of search results coming back from here. And then we go ahead and we return the results. Now, in real life, I was doing this just so I could show you the steps, but in real life, we would probably say return m words to find .stream .map .filter .collect. We wouldn't have a separate variable here. These are intermediate operations. They run when the terminal operation is reached, and that'll cause the processing of the stream to take place. So you can see here that if you look at the code, here was the code that called all this stuff, right, back here. So we said, take all the input strings, turn them into a stream, call process input on each input string to find a list of search results. We ignore the ones that don't match, collect it into a list, right? Totally declarative. Process input, that's what we just looked at here. Once again, totally declarative. So you just read it. Again, when you're first exposed to this stuff, you're like, what the heck is going on? But once you get used to it, it's really concise, and it's only focusing on the computations to perform, the order those computations are performed, and the transformations that take place, or the filtering that takes place as the data flows through that stream and is modified. Now, the other thing you'll note, this particular example is a good example of this, there's no side effects. So all of these things are just functions, and they're taking in streams, and they're returning streams, and so on. Or they're taking an input, and they're returning output. But there's no state that's being stored anywhere. So as a result, this type of code is trivially, embarrassingly parallel, and therefore incredibly easy to parallelize. Yes?
So if we put other functions in the collect, we can get other types of collections that are results?
So here, you're talking about this? Yeah, so you can collect, here we're collecting to a list, but you can also collect to a map, and you can, it's an open-ended API, so you can collect to whatever data structure you want if you're willing to write some additional code. And then the other thing we'll talk about later is we can add additional processing steps or intermediate operations, and as long as they obey the input-output rules of our stream, you can superimpose them or interpose them here without changing anything. So it's really easy to modify your code without having to do a lot of work, which is really cool. OK, let's see. So kind of summarizing this, there's a couple of things that are interesting to note about this. One thing to note, and we'll talk about this more next time probably, the streams use internal iterators versus the external iterators you're accustomed to working with containers. So if you work with normal containers, you're accustomed to using a for each loop on the container. Streams don't do that. They use internal iterators, and there's certain pros and cons of that, which we'll talk about in more detail. The main thing that's a pro here is that the internal iterators shield the programmers from any knowledge of the way it works under the hood, what's happening. And you can see that the processing pipeline is highly declarative. You just say what you want to have done. You don't say how to do it. It knows how to do it because it's based on streams. And so you're focusing on the why or the what, not the how. And you'll also notice that these Lambda functions here have no side effects. They do all the work on their parameters and return a result, and that's then used in the next step. One of the things that took me a little while to get my head around at first, but when you think about it, it's really obvious. When we talk about map or filter, we talk about those as being aggregate operations. What does that mean? What it means is that it's actually taking a stream of data. And so if, let's say, the stream has n items in it, map is going to do n things on those items. So it's aggregating what's passed to it. So it looks like a single function call, but it's actually just transforming every element in the stream by calling this Lambda expression on each element in the stream. So it's an aggregate of operations and steps. For some reason, that took me a while to figure that out. No side effects make it easier to reason about behavior and enables optimization. Let's see if I talk about the optimization here. So I don't show it here. We'll talk about this later. If I wanted to convert this program from a sequential stream to a concurrent stream, because of the fact it has no side effects other than just the processing that's taking place and being returned as values, all I would have to do is replace .stream up here with .parallelstream. And .parallelstream basically says, underlying system, you figure out how to run this thing efficiently in a multi-core or multi-threaded environment. And so all the threading, all the concurrency control, all the management is handled by the internals of the streams framework. And all you have to do is just say, I want this stream to run in parallel. Now that kind of transparent optimization only works if you have no side effects. If you have side effects, then things fall apart very quickly, and you have race conditions and so on. And you have to protect your data with locks and so on. But if you don't have that, as we do here, we don't have that problem, then going from a sequential stream to a parallel stream is as easy as changing this to .parallelstream. Now, it turns out that there's other things you can do as well that sometimes work faster and better, but this is a really easy way to take advantage of concurrency. Under the hood, the parallel streams mechanism uses the fork join thread pool that's part of the Java executor framework, and it also uses something else called a splitterator to split the data up into parts. This example only used a few aggregate operations. There's lots and lots and lots of them. You can take a look here at this link to find many, many, many more of them. And we'll talk about a few more of them as we go through this stuff. In particular, there's another example called the image StreamGang that applies a few more things and does image processing and so on. I've got a cool set of videos that talk about all this stuff. There's also other videos you can take a look at online that talk about Java 8 streams and Lambda expressions. And I highly recommend you take a look at this book, which is called Java 8 in Action. This is where I learned everything I know about streams. And the authors do a great job of explaining what streams are. And they also have a number of online articles that summarize some of the key points in the book. The book is fantastic. It goes into great, great detail. They also have a couple of articles, this one and this one, that talk about some of the streams topics and talk a little bit about some of the concurrency issues, which are covered much more in the book than they cover in their online articles. But that's where I learned all this stuff. I learned it last summer. It took me pretty much all summer to really get my head around it. But it's a lot of fun, and it's definitely the way the world is going in terms of concurrent programming and things like that. All right, so that's the end of that.